Welcome to Module 9. In this module, we focus on how solar inverters protect themselves, protect the system, and comply with modern interconnection standards. We will explore coupling architecture, inverter topology, MPPT behavior, voltage and current limits, control models, protection coordination, and real-world case studies. By the end, you will understand how inverter protection shapes the entire design workflow for solar plus storage systems. Coupling architecture defines how the PV array, inverter, and battery energy storage system interact. In AC coupled systems, the PV inverter and PCS operate independently on the AC side. In DC coupled systems, both share a common DC bus. Each architecture affects power flow, protection strategy, MPPT behavior, and compliance requirements. Choosing the right architecture is one of the most important early design decisions. Modern solar inverters use advanced semiconductor topologies to manage DC to AC conversion efficiently and safely. String inverters distribute risk and simplify protection, while central inverters consolidate control and reduce balance of system cost. Hybrid inverters integrate PV and BESS on a shared DC bus. Understanding topology helps engineers predict fault behavior, thermal limits, and compliance constraints. The PCS DC bus voltage decides how much the battery can charge or discharge, and whether the PV array voltage fits efficiently within that range. MPPT behavior changes significantly depending on coupling architecture. In AC coupled system, the PV inverter performs MPPT independently, and the PCS manages battery charging on the AC side. In DC coupled system, MPPT must coexist with battery charging on the same DC bus, which can shift operating points. Engineers must ensure the MPPT window aligns with both PV characteristics and battery voltage ranges. Every inverter operates within strict voltage windows. This includes the MPPT voltage range, maximum DC input voltage, AC output voltage tolerance, and DC bus limits for DC coupled systems. Cold with open circuit voltage, hot with maximum power point voltage, and battery charge voltage all interact. Proper voltage window analysis prevents nuisance trips, protects semiconductors, and ensures compliance with grid coders. If the PV array's operating voltage is lower than the PCS minimum, the system cannot transfer power efficiently. That's why DC coupling is not recommended in this case. Current limits protect inverter switches and magnetics from overload. PV array current, PCS charging current, and AC output current must all remain within manufacturing limits. Overcurrent conditions trick protection responses such as clipping, curtailment, or shutdown. Engineers must size conductors, fuses, and breakers to match inverter current behavior and both normal and fault conditions. Inverters operate in multiple control modes depending on grid conditions and system requirements. Grid following mode synchronizes to the grid and injects controlled current. Grid forming mode established voltage and frequency, enabling microgrid operation. Additional modes include charging control, discharging control, curtailment, and black start. Those modes define how the inverter behaves during disturbance and protection events. Protection coordination ensures that faults are detected, isolated, and cleared safely. Inverter-based resources contribute limited fault current, so traditional protection schemes must be adopted. Engineers must coordinate DC side fuses, AC breakers, ground fault protection, and PCS protection logic. Proper coordination prevents cascading failures and ensures compliance with utility protection requirements. In AC coupled systems, both the PV inverter and the battery contribute fault current on the AC bus. In DC coupled systems, the PV fault current is much lower because it's limited by the DC bus and converter. Inverters generate harmonics due to switching behavior. Excessive harmonics can cause overheating, misoperation of equipment, and non-compliance with IEEE 519 limits. Engineers must evaluate total harmonic distortion, switching frequency, field design, and the interaction between PV inverters and PCS units. Good power quality is essential for grid acceptance and long-term reliability. Communication links allow the inverter, PCS, EMS, and the utility to coordinate operation. Common protocols include Modbus, CAN, and Ethernet-based systems. Control commanders manage real power limits, reactive power support, ramp raters, and protection settings. Reliable communication ensures the plant responds correctly to grid events and meets interconnection requirements. Efficiency varies between AC coupled and DC coupled architectures. AC coupled systems experience multiple conversion stages, while DC coupled systems reduce conversion losses during battery charging. Engineers must consider MPPT efficiency, PCS efficiency, idle losses, and round-trip efficiency. The right architecture depends on project goals, load profile, and regulatory requirements. Reliability depends on thermal management, electrical stress, environmental conditions, and components aging. Inverter must withstand temperature swings, dust, humidity, and long-term cycling. Proper derating, ventilation, and maintenance planning extend inverter life. Reliability is not just a hardware issue, it's a design philosophy. Always verify inverter DC bus limits before selecting coupling architecture. Avoid PV array maximum power point voltage too close to PCS minimum voltage. Oversize PV only when the MPPT window supports it. Confirm PCS charge current does not exceed inverter DC current limits. Ensure grounding schemes are compatible across PV, PCS, and transformer. And always validate protection settings against utility requirements. In this AC coupled example, the PV inverter and PCS operate independently on the AC side. Power flows through the AC bus, allowing flexible operation, but introducing additional convection losses. Protection relies on AC breakers and coordinated inverter logic. This architecture is ideal for retrofit and systems where PV and BESS operate with different schedules. In this DC couplet example, the PV array and battery share a common DC bus. The PCS manages both charging and discharging directly on the DC side. This reduces convection losses and improves charging efficiency. Protection must account for DC bus faults, battery voltage ranges, and MPPT interactions. DC coupling is ideal for utility-scale systems focused on maximal energy capture. Before commissioning, verify voltage windows, current limits, grounding, communication linkers, and protection settings. Perform insulation resistance tests, polarity checks, break coordination checks, and EMS command validation. Confirm MPPT behaviors, PCS charge control, and grid support functions. A thorough checklist ensures safe and compliance operation from day one. When selecting a coupling architecture, always start with voltage window alignment, confirm protection coordination, and aim for the highest efficiency within inverter limits. In this module, we exploit inverter protection, coupling architecture, topology, MPPT behavior, voltage and current limits, control models, harmonics, communication efficiency, reliability, and real-world case studies. Those concepts form the foundation of safe, compliant, and high-performance solar plus storage design. In the next module, we apply these concepts to advanced design workflows, including inverter selection, base sizing, and system optimization. We will walk through real project examples and show how engineering decisions impact performance and compliance. If you found this module helpful, please consider liking the video and subscribing to Gamma Classroom. Your support helps us continue producing high-quality engineering content. Thank you for watching Module 9. See you in the next module.